In science, no theory is immune from one day being overturned, even if it has been integral for a very long time. Isaac Newton, for example, first theorized the existence of something called ether, a seemingly magical substance that Newton suggested was what filled the emptiness of space, giving waves, including light, a medium to travel through. And the idea largely held for hundreds of years thereafter, until one Albert Einstein finally explained ether away. A one-time pillar of science had been knocked down and reimagined. But now, fast forward to today, and could something similar be happening all over again? This is Unveiled, and today we're answering the extraordinary question, did scientists just discover that particle physics is wrong?
Do you need the big questions answered? Are you constantly curious? Then why not subscribe to Unveiled for more clips like this one, and ring the bell for more thought-provoking content.
There are many theories in science that we think are mostly right, but not quite perfect. Einstein's theory of general relativity, for instance, is held to be one of the most ingenious out there, but we know it's incomplete. Although it explains a huge amount about gravity and space, it still falls short regarding quantum gravity and singularities, like those that form in the center of black holes. The same can be said about the standard model of particle physics, that it's good, but not quite perfect. It's the most successful framework we have to broadly describe the way our universe works, explaining how all particles link to four fundamental forces: the strong and weak nuclear force, the electromagnetic force, and gravity. The model pitches that these forces are what allow elements to form, and they dictate how particles interact. But the standard model also isn't complete, and science knows this. Despite it explaining three of those four forces extremely well, it has yet to effectively incorporate gravity. It also fails to allow for dark matter, to some degree antimatter, and other important unknowns in astronomy. One of the ways in which the standard model is continually tested is with the help of atom-smashing particle accelerators. These incredible machines, the most famous of which is the Large Hadron Collider beneath the France-Switzerland border in Europe, are used to accelerate beams of particles to intensely high speeds, sometimes getting close to the speed of light under routinely extreme conditions. In general, the matter within the accelerators is propelled to these speeds in order to achieve high-energy collisions, which smash apart protons, or whatever's being tested, into a cloud of different, often rarer, subatomic particles. For science, it's like breaking into the subatomic world. And by watching these interactions, researchers can test predictions and, hopefully in some cases, find new particles. In 2012, the famous detection of the elusive Higgs boson particle, said to be what gives mass to all other particles, was for a time thought to have rounded off the standard model, filling in the last great puzzle piece within it. But now, all confidence is out the window, as new research is threatening to totally upend the model, irrespective of the fact that it's been a cornerstone of modern science for decades. For the most part, the standard model has proven good at predicting things like particle mass, weight, and general behavior, but apparently not this time, after a discovery announced in April of 2022 regarding a particle called the W boson. W bosons are important in physics because scientists think that they, with the help of Z bosons, give rise to the weak nuclear force, the force responsible for radioactive decay in atoms. The paper detailing the discovery, published in the journal Science and relating to a decade-long study by a team at Fermilab in the US, found that the W boson in particular is slightly more massive than would be expected or predicted by the standard model, about 0.09% more massive. And while that may sound a little underwhelming, extreme precision is vitally important in subatomic study, and even the tiniest of variations can make or break a theory. And so, despite the discrepancy being small, the results are statistically significant, implying that something's gone awry. Either the method and measurement or the standard model itself is in error. Particle physics until this point, then, really could be thought of as wrong. This isn't the first time the W boson has been scrutinized. Researchers first found the boson and recorded its mass back in 1983, and at the time, the data matched what was expected of it. The particle was found to fit within the standard model. Times have changed, however, and the new boson measurement is the result of 10 years' worth of work and countless particle collision tests. In fact, those behind the 2022 study claim that the new measurement is more accurate than that obtained from all previous W boson experiments combined. And while 10 years of analysis toward one subatomic particle might feel like a lot, a member of the project, the physicist David Toback, has reportedly said, quote, "You can do it quickly, you can do it cheaply, or you can do it right," end quote, before claiming that they did it right. It would appear then that in this case, neither the method nor the measurement is at fault, which means only the standard model itself is left wanting. Due to its wide-reaching repercussions, this seemingly tiny W boson revelation has sent shockwaves through the scientific community. There have already been some theories put forward to try and explain the W boson's mass while preserving the standard model, including a suggestion that there could be a problem with how we understand that other poster particle of 21st century science, the Higgs boson. But so far, nothing sticks. To some degree, this could prove to be the first major blow to the standard model since its creation in the 1970s, although it should also be noted that not everyone is quick to completely write it off. At what's still an early stage in science's bid to process what has happened, many are taking the new boson results with a grain of salt, at least until they're confirmed by follow-up tests. A claim as heavy as this certainly requires a lot of investigation before it's universally accepted, and researchers, including those across the Atlantic at the LHC, are already working toward that. But it's expected to take time. W bosons are notoriously difficult particles to pin down for a couple of reasons. First, they rarely appear, with it reportedly taking literally millions of collisions during the Fermilab tests between protons and antiprotons to produce just one of them. But second, they're also extremely short-lived, disappearing before they can even be directly measured at all, as researchers usually have to chart them based on the energy trail that they leave behind. Really then, this story already represents an impressive enough breakthrough based just on the fact that science can now get any kind of handle on these things, when for so long they had been essentially inaccessible. But the discovered discrepancy on top of that makes it all the more important. So what happens next? Armed with and inspired by the new, ever so slightly more massive measurements, scientists will now strive to work out why the W boson doesn't fit with how we thought things should be. What specifically sets it apart? What specifically is lacking with our current model of particle physics? And what do we need to change to improve it? Because although research like this might at first feel like a disappointing result, and although it may make it appear as though science has failed us until this point, it's actually the opposite that's true. Thanks to improved study, we now know that there's more we don't know about the universe. And that paves the way towards opening new doors, bringing in fresh perspectives, and potentially gaining a better, truer grasp of reality than ever before. At the subatomic level, the present perhaps isn't quite what we had previously expected it to be, but the future remains bright. There's a fresh challenge laid out in front of us, and this new research might be exactly what science needs to progress. This one discrepancy could well force physics into developing a new standard model, which could fundamentally improve the base knowledge of our entire species. That's why this tiny measurement is also huge news, because of the wider implications that it could have, because of the changes it could trigger, and the answers it might reveal. What's your verdict? What does the W boson tell us about the wider world around us? Is the standard model still strong enough for purpose, or does this one hole weaken it beyond fixing? The debates are sure to rumble on, and the follow-up tests are already underway. But that's how scientists may have just discovered that particle physics is wrong.
What do you think? Is there anything we missed? Let us know in the comments. Check out these other clips from Unveiled, and make sure you subscribe and ring the bell for our latest content.